Hi everyone, Radko Tuta here explaining. In this video, we are going to look at analytic functions. So what are these analytic functions? Analytic functions are simply functions that are entire. So functions that are entire are said to be analytic functions. And then these analytic functions, for you to say that a function is analytic, meaning it must satisfy the Cauchy-Riemann's equations. So functions that are analytic, they always satisfy the Cauchy-Riemann's equation. And what are the Cauchy-Riemann's equations? The Cauchy-Riemann's equations are that for a function which is analytic, it should satisfy the conditions such that sigma u over sigma x should give you sigma v over sigma y. Not only that, but also sigma v over sigma x must be equal to negative sigma v over sigma y. So for you to prove that a function is analytic, meaning you are supposed to show that that function is satisfying these CR equations. So these equations are the ones that we call as the CR equations, which are also said to be the Cauchy-Riemann's equations. Now, let's have an example and see how we can prove that a function is analytic or it satisfies the CR equations. So, our first example is coming from a book called the HKDAS. So we have our first example here, number one, which is saying that show that the function, so they want us to show that the function f of x equal to e to the power x open cos y plus I sine y is analytic. So for you to show that that function is analytic, meaning we want to show that it is satisfying the Cauchy-Riemann's equations, which are these. So let's do that. So we are going to say, for you to show that it is satisfying the Cauchy-Riemann equation, meaning you're supposed to differentiate x in the u, y in the v, x in the v, and y in the v. Now for you to do that, you are going to say solutions. Our f of x is given to be e to power x open cos y plus I sine y. So what we are going to start doing here is to first multiply the e which is outside with what is inside there. So we're going to have our f of x is equal to e to power x cos y. If we have to multiply the e with what is here, then we also multiply this times that, which is going to give us plus e to the power x I sine y. Now, since one part is having a complex part and another one is having a real part, meaning that we can separate this function into two. How can we separate? We can say let u to be equal to the real part. So we can say let u to be equal to the real part, which is e to power x cos y. And the v to be equal to the imaginary part, which is e to power x sine y. Like that. Then from here, remember we are getting these parameters such that we need to get these parameters here. So we'll start by differentiating x in the u and the y in the v. So let's do that. All right. Now, what we're going to do is we are going to say we differentiate x in the u. What is our u? Our u is here. So we differentiate x. So we say sigma u, we differentiate x. We are going to differentiating x here. It will remain e to the power x because differentiating e to the power x, it remains e to the power x, and then the cos y remains constant. Then from there also in the u, in the v we can differentiate y. So in the v we can differentiate y. Where is the v? V is here. So in the v we are differentiating y. So differentiating y, we are going to keep the e to the power x constant, and differentiating sine y you get a cos y. Right. Then from there, we also need to go to the other conditions where we are saying that in the v, we need to differentiate x. So in the v, we differentiate x. So differentiating x in the v, where is our v? Our v is this one here. And we are differentiating x. So differentiating x there will say sigma v over sigma x is equal to, we are differentiating x. So differentiating x here in the v, we are going to keep it the way it is, which is e to power x, and the sine y remains constant because these are partial derivatives. The last part is that in the v, we are supposed to differentiate y. So in the v, differentiate y, meaning that we're going to say sigma v over sigma y is equal to differentiating y, meaning that the e to the power x is constant, and differentiating y in the v, meaning that you are going to remain with a negative sine y. So we're going to get a negative here, then sine y. Right. So that's what we've gotten. Now, after you've done that, what you're going to do now is to compare with the CRI equations. Remember, the CRI equation says that for a function to be analytic, meaning that sigma u over sigma x should be equal to sigma v over sigma y. So you need to check, is the sigma x that you've gotten, is it the same as that you are getting when you differentiate y in the v? Yes, for sure, because we've seen that sigma u over sigma x is this, and sigma v over sigma y is that. These are simply the same answers, meaning that the first condition has done what? Has held. Then we also need to see that the second condition says that sigma v over sigma x must be equal to sigma v over sigma y, but with a negative in front. So we are going to say that our sigma v over sigma x should be equal to negative sigma v over sigma y. So let's check, what is sigma v over sigma x? Sigma v over sigma x that we've gotten is this one here, which is e to power x sine y. So you write it e to power x sine y. Is it the same as negative outside with sigma v over sigma y? What is sigma v over sigma y? Sigma v over sigma y is this one, which is negative x e to power x sine y. So you write negative x e to power y, negative e to power x sine y. Now here we have e to power x sine y is equal to negative, negative is positive, so we are just going to remain with e to power x sine y. So this tells us that for sure this sigma v is equal to negative of sigma v over sigma y. So both conditions, this one and this one, has held, or they are satisfied. That means that for sure this function given here is analytic because it is able to satisfy the two conditions for an analytic function. All right. So now that's how you prove that a function is analytic. So you just say since sigma u over sigma x is equal to sigma v over sigma y, this is equal to that, or and sigma v over sigma x is also equal to negative sigma v over sigma y. Since these two functions are equal, therefore the function is entire. So you can say therefore f of x is analytic like that. So that's how you prove that a function is analytic. Thank you so much for watching my videos. Please don't forget to follow my Facebook page. Invite more people to follow the page for more videos and tutorials. See you next time.